All right, hi everyone. Welcome to the Project 5 overview video. Congrats on finishing the midterm. Unfortunately, you don't have any time to rest because technically the midterm week was the week off. So it's time to do Project 5 now, and it's due next week. Project 5, I think, is significantly more challenging than Projects 3 or 4. Maybe not as hard as Project 2, but what makes it hard is that there is a very large code base. There's a lot of different classes that you have to get used to. So that's what makes this project difficult. But I'd say this is probably the most interesting project we've done so far. Jerry also agrees. So we were pretty excited to go through this project with you. Okay, you'll learn a lot about demand paging. Okay, so this video is going to be very long. Okay, in fact, I'm going to split it up into 3 videos because I'm not going to cover everything in a single video. So what the 3 videos are going to be is the first video is going to go over just quick review. What is demand paging and how does it apply to this project called memory mapping? This project is dealing with mmap, memory mapping. Then we'll go over both what demand paging looks like from the programmer's perspective. Okay, it's pretty boring, but I want to go over it. And then we actually uncover what happens underneath the operating system that allows demand paging to happen. So we'll look at the physical memory and the page table. In the third video, we will then go over I skipped video 2. In the second video, we will go over we'll review how do you actually implement each of these functions. Okay, we'll go over conceptually how it works, then we'll talk about what each of these functions that you have to implement should be doing. And then we'll take a look at the starter code. From that point forward, you should be able to pass all of the tests. Okay, even though I will suggest a few simplifications you should make so that you can pass all the tests. Then in the third video, we will be less wasteful with our implementation. Okay, and then when that happens, the tests should still pass, but you will just be less wasteful. Okay, so remember, you're not done even if all the tests pass. Okay, you still have to implement an extra part about flushing and about permission, about protection. Okay, so we will implement that at the very end. Before we get started, I want to encourage all of you to pause the video and spend an hour going over the starter code, because one of the big goals of this class is to get you super used to dealing with large code bases, because in future CS classes or in research or in an internship, you'll often have to deal with large code bases. And this class was the class where I learned to dig through a bunch of many different files to figure out what I was supposed to use. Okay, so recommend that you spend an hour or so, try to figure out this assignment on your own. And then once you get stuck, then come over to the video and we'll go over what this assignment is all about. Okay, so now that you've done that, which I know all of you have, let's go over memory mapping. So the easiest way to explain memory mapping is to talk about what it looks like, right? What happens when you try to memory map a file? Okay, so this chunk of our code over here, this is using the mcrypt file class. You are implementing the mcrypt file class. You aren't writing this code. This is the test harness code. We're going to look at this from the perspective of the user, so of the virtual memory. Okay, remember, when you are programming in, let's say, CS107, all the arrays and the pointers that you're dealing with, the addresses there, they're all virtual addresses. So when you are memory mapping a file, the operating system gives you the illusion of a certain layout of memory, even though behind the scenes, that's not what memory actually looks like. Okay, so let's first look at that perspective. You have an mcrypt file 1. So this is the constructor. We declare it, we pass in a key. You don't have to worry about the key at all for this assignment. And we pass in a file name called book.txt. So let's assume this is a big book. And how many bytes does it have? It has 7 times 4096 bytes. Okay. Now, we'll be dealing with pages in this project, and pages are, for this project, always in multiples of 4096. So one page is 4096 bytes. Even for the files itself, the file isn't technically in pages, but we're going to think about them in pages. Okay, so there's like 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Let's 0 index. 1, 2, 3, 4, 5, 6. Okay, so that's a page. Each of these are pages. That's a file. This is called book.txt. Okay, so when you create the mcrit file, you haven't done anything yet. Okay, we just know that there's a file here called book.txt. The magic comes when you call the map function. You pass in the parameter 40,000. That stands for 40,000 bytes. And what should happen is that in virtual memory, you now have this gigantic array of 40,000 bytes. This is 0. This is 40,000. And the idea here is that this function outputs a pointer, right? That's what book here is. Book is pointing to the beginning of this array. This array should now be filled with the contents of book.txt. Okay, so book.txt will fill all the way up to here, 4096. Okay, now note the actual file is not 40,000 bytes. It's only 7 times 4096 bytes. So there's a bunch of extra space down here. Okay, and that's it. This is what it looks like in virtual memory. When you are programming, when you memory map a file, you can just imagine that you have a long contiguous array that contains the contents of the file. So we can go into, say, byte 5,000. So that's somewhere here. And we can read a single character. You can print it. Okay. Yeah, we're just imagining that this entire file has been put into memory in a long contiguous array. Okay, let's do one more. So we call recipe.txt. So you can imagine this file is much smaller. So let's make it smaller. There's a file called recipe.txt, and it's a small file. .txt. Let's say it only has 2 pages, 0 and 1. Okay, so what you should imagine in memory is there is a contiguous file. Notice here we pass in 0, but that's not allowed. Well, the function does work, but what happens here is that the map function, if you give it a number that is smaller than the size of the file, it doesn't care. It will still map the entire file for you. Okay, so you can request extra space. If you request space that's smaller than the page of the file, it will just round up to the size of the file. So here, if this file was, let's say this file was like 6,000 bytes. Okay, so it doesn't necessarily have to fill up the whole page, but just it spans 2 pages. One page is completely full, the other page is like half full. Then it's gonna allocate 0, 6,000 bytes. And it's going to fill the contents here with the contents of the file. So let's say this file here, it will fill it up like that. Filling up the entire thing, there's no empty space at the end. Okay, and that's it, right? This is the pointer that's returned is recipe. You can try to read this long array, read index 5,000. So we go to 5,000 and we read, well, we don't read it actually, we set it to Q. So this thing becomes Q at index 5,000. Notice that we don't write back to the file yet. Okay, you modified it in virtual memory, but you do not write back to the file yet. Now memset. So memset, we do book file plus 6 times 40996. So that's somewhere here. Let's see, orange. That's book file, not book file, just book. Book plus 6 times 4096. And then we're going to write 5,000 X's. Okay, so the X's are going to span X, 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 X. They're going to completely cover this region. And it spills over to here, and it writes 4 extra X's. Right, it spills over past the end of the file. We allocated space for like more than the file, so that's fine, but we just wrote past the end of the file. That's totally fine. later, we're going to call flush. So mem set, we're going to call flush on m file 1. Okay, when you call flush, what happens is that the contents of this book, or rather the contents of this array, gets written back to the file. Ooh, here. The contents here get written back to the file. Okay, let's see. I actually don't remember if this part gets written to. Let me check. I don't remember if that part gets written to. Extend. If the bytes are written to a region beyond the original file length, the file will be extended when flush is called. Okay, well, not a big deal. Not a big deal if I believe the whole thing is written. I'm not 100% sure, but honestly, the starter code handles all of that. You don't have to worry about that case. Just when it gets mapped, you just write as much as you can in here, and then when you're done, you just call. You just write the entire thing back into the file. That might end up extending the file. All right, and we're mostly done. Yeah, we flushed everything into the file, so now the file is changed. There's a bunch of X's at the end. The file has been extended a bit. Now we just have to think about what happens at the end. Well, here, let's call file 2.unmap. Okay, so unmap is simple. Unmap is first flush everything. So I write the Q into the file, and then just remove the virtual memory, free it completely, so it's gone. That's it for unmap. Finally, both of these go out of scope. So m file 2, it goes out of scope, doesn't matter because you have nothing. It has nothing in it anymore. M file 1 goes out of scope. The same thing as unmap. You write everything to disk, to the file, and then you just free up your virtual memory, so it's gone. Okay, it's kind of like free. Virtual memory no longer exists anymore. You can't use that pointer anymore. All right, so that's it for what memory mapped files look like. Right, this is how you use memory mapped files. From the user's perspective, the map function outputs a pointer that points to the beginning of a long contiguous array. Okay, and you do not have to know anything about how that array is secretly handled. You can just use it in your program as if it was a long contiguous array. All right, now that you know how memory mapped files work, let's now uncover what happens inside the operating system to make this work. So I'm still going to refer to this code, but I'm going to need a little more space. So let me actually copy everything back. I'm going to need a little more space. So I'm going to use the next page, but I'll come back and refer to the code frequently. Let me actually just, let me come here. Okay, so we're going to create a mcrypt file, m file 1. So let's create it. Now, when you call the constructor, we say book.txt. So this is linked to some book, some text called book.txt. Okay, but when the constructor gets called, nothing actually gets allocated inside, right? There's no virtual memory region. What you should do is this VM region you're going to declare it as part of your mcrypt class. I recommend that you declare it as a pointer to an mcrypt region. Okay, so technically the mcrypt region will look something like that, but just to save space, I'm gonna just write it like this. So later I'm gonna map it down into a region down here. But for now, when the constructor gets called, these should just be null pointers. They should not be mapped to anything. Next, okay, yeah, so that is the first step. The constructor just connects the file to the mcrypt file, but it doesn't actually map any virtual memory. It's only when you call map does the virtual memory get mapped, right? You can only initialize your virtual memory after map is called because you need this 40,000 to know how big your virtual memory should be. Let's actually make this a little smaller. So this virtual memory, it was previously a null pointer. Now it becomes a pointer to a VM object that can be represented like this. Yeah, let's write it like that. So VM object. Okay, and you can visualize that the VM region is just a long contiguous array, just like what we had previously. Now we said 40,000. So what is 40,000? 40,000 is, I believe, 9 pages. So let's split that into 9 pages. And then let's give these an address. So let's call the first one 0x470000. Okay. Now, because each page is 4096 bytes, 4096 is actually 0x1000. So if the beginning of the first page is 0x47000, we know that the next page is going to be what? It's going to be 0x48000. The beginning of each page is always ends in 3 zeros in the address. Okay, that's pretty nice. If you need to find which page you're on, just clear out the last 3 zeros. Or in hex, the last each 0 is represented by 4 bits. So you actually clear the last 12 bits. So I'm going to write this as 4849, just so I don't have to write too many zeros. But remember that each of these are addresses. They have 3 trailing zeros. These are also hex digits, so I have to write them in hex. Okay, so that was the VM region. Now, in your mcrypt file, you can easily check what the size. So there's, I believe there's a get base function, and there's a get size function. Okay, these are functions. But if you call get base, what do you think is returned? It should be 0x47000. If you call get size, what should be returned? It should be 9 pages, so 9 times 4096. Okay, so that is what the map function does. Now, the map function also does something special. In the very first call to map out of any mcrypt file, not just this mcrypt file one, but any mcrypt file, if you call map, you have to allocate physical memory, because later we have virtual memory right now, but we're going to need a space to put the physical memory in. So in the very first call to map, you both map the VM region for this mcrypt file, but you also allocate a physical memory space for all of the mcrypt files that's shared among all mcrypt files. Okay, so let me draw a line. So here's physmem. Actually, maybe I don't want to write up here. I'm going to save this space for something else. Physmem. Never mind, I changed my mind. There's 3 data structures I have to write here, so I'm trying to figure out how to save space. So here's physical memory. I'm going to make it simple. I'm just going to have 4 different pages in physical memory. Let's give them addresses: A1000, A2, A3, A4. Okay, they're all 4096 bytes. Okay, now this should be a static variable. Okay, so in fact, I think it's better if I wrote it like this. So this is like static variables. You have one that is a physmem. Initially, you have a physmem pointer that is the null pointer. And then upon the first call to map, you both map the VM region that is one per mcrypt file. You also have a physmem that is shared among all of the objects. Okay, so I'm only going to create one of these. Later, I'm going to create an mcrypt file 2 down here, but the physmem is a shared static variable among all of the mcrypt files. Now, physmem has a couple special functions. it has a function called pageAtloc. Which finds an empty page and returns it so that you can use the page. It also has a page free that we'll get to later. All right, so these are the two steps that you need to do for the map function. Now, in the map function, when you initialize the VM region, you're going to have to add something called the page fault handler. So let's talk about what the page fault handler is. The page fault handler is called when you try to access virtual memory that has not been mapped to yet, right? We have not taken anything from the file. We have not placed anything from the file into physical memory, right? The only way to read like memory read from the memory is to move from the file into the physical memory. The virtual region is an illusion. The bits don't actually go there. Instead, this is what the programmer thinks the memory is laid out as, but in fact, there is a translation from the virtual memory to the physical memory, right? Remember, that's called the page table or page map. So let's write the page map. So page map, I'm gonna write it as green. Okay, you might be wondering why I'm repeating colors. It's because the page map is actually a static variable shared among all VM regions. Okay, so important, there's only one page table that's shared among all of the mcrypt file classes. I'm gonna draw it in a cloud because this is secret. What I mean by secret? You can't go into this page table and actually read it. Okay, so it's a table, it maps virtual pages to physical pages with a protection bit and a present bit. Okay. It's a secret table because you can't actually read from it. You can modify it though. You can modify it by calling the static functions VM region, map, and unmap. That's how you modify this table. But you can't read through it. That's actually going to be an issue later. In fact, instead of telling you that later, I'm just going to tell you it now. You can't read from the page map, but you would really like to access the page map. So what do? You make a copy of it yourself. So let's call this the supplemental page map. Sometimes it's also called the auxiliary page map or auxiliary. Don't know how to spell that word. And it's basically a copy of that. Now you might be wondering, why do we need the page map and the supplemental page map? The page map is secret. It's private to the operating system that is actually handling the translation, right? It's the MMU that's handling the translations between the virtual address and the physical address. You don't have to handle the translation yourself. You just have to update the page map. And whenever an address needs to be translated, the OS will look at the page map to handle it for you. Okay, but this is otherwise private. You can modify it, but you can't read from it. But we do want to know which pages we have added to our page map. So to know that, we just store a separate copy of it. Okay, but I'm going to add an extra field to it. So prot present. Let's add two fields. Let's add a dirty bit and a bit, let's call file. Okay, we'll talk about why we need each of these later. All right, so auxiliary page map. This page map should be a static. It's shared among everything. So you can imagine there's a sup page map. That's just this thing. Okay, it doesn't have to be a pointer because You don't have to initialize it to null pointer. You can just create the map upon just statically initially. Okay, just create the page map, the supplemental page map. The page map you don't create yourself. You can modify it, but you don't have to create yourself. It is already created by VM region. All right, now that we have all that set up out of the way, now we can finally talk about the page fault handlers. So here, book, remember the pointer to book was 0x47000. So this address, book at index 5000 would be in address 0x47064. Okay, 64 is just, sorry, not 64. It would be 4. So 47004, right? It's 4 bits off of 4096. My bad, not 4748. Because 5000 in hex is 1004. All right, so here we are trying to access 0x48004. Now I want you to all remember to review this. What happens when you try to access an address? What happens is you go to the page table. Actually, there's one step before that. Before you go to the page table, you first figure out what page you're in. Okay, so given this address, what page are you in? So address translation 48004. What page are you in? So this is the address. The page would be 0x48000, right? Clear out the last 3 bits. That determines, not last 3 bits, last 3 hex zeros, last 12 bits. That's what determines what virtual page you're in. So you're in this page. Then you check if it's in page table, page map, right? Because you now have the virtual page. To figure out where the data for this virtual page is stored, you have to figure out what physical page it's stored in. So we go to the page map to determine which physical page it's stored in. And we see that it's not in the page table. So not in page table. That generates a page fault. And the page fault is the one that's responsible for paging in the, or rather reading page in to physical memory. And it also has to update the page map. Okay. So there's no mapping right now, but once you read the physical page into physical memory, once you read the page from the file into physical memory, now you can add a mapping so that future reads will be able to find the correct physical page. So here, there's nothing in the map, so we generate a page fault. What should the page fault do? What should the page fault handler do? I don't have any space. Let's write something down here. Page fault handler. Okay, so what happens to page fault handler is we get the faulting address. Faulting address. What are the steps? Okay, so try to review from the notes, pause the video, try to review what the steps are. This is on the final, so make sure you know the steps. All right, what's the steps? First, as always, you get the virtual page, right? Everything is done in terms of pages, so you always first get the page. Now, what you do is you know that what page it is, but you know that it's not in the page map, so it's not in physical memory. So we need to put it in physical memory. Before we go to the file and actually bring stuff into physical memory, we need a page from physical memory. So allocate a p page, and you do that using the page alloc function from the physmem class. Okay, so let's say we allocate a physical page and we get orange, we get 0x, let's say we get A1000. Okay, now what is the next step? There's 2 steps we need to do. One is we need to update the page map to map 0x48000 should get mapped to 0x81000, right? So 0x48000 should get mapped to 0x4100. Did I say 41? Oh, A1. A1000. Protection. For now, we're just going to use read-write protection. And then present, yes, 1. Now, what do you think the supplemental page table is? Well, we can't read from the page table, but we're going to need this information to be stored into the page table. So what we do is we just, any change you make to the page table, just add a separate change to your supplemental page table. So 48, x81000, read write, present. For now, just set the present in dirty bits to what you want. And what file that it came from? M file 1. So let me just record that. You'll see why this is helpful later. Okay, so we have now allocated A1000. We have updated the page map using VM region : map. Okay, there's one. Oh, also update sup page table. All right, there's one more step we have to do. Right, we've allocated all the space, but we haven't actually go to the file and brought the contents in. So here is where we go to the file and we bring the contents into here. Oops, into here, the page that we allocated for it. So last step, bring contents of file into physical page. Okay, now how do we do that? First, what part of the physical page, what part of the file are we reading in? The beginning, the end? How do we know where in the file to read in from? Well, if you look at this picture, this green array here, we know that the very beginning is the start of the file and the very end is the end of the file, right? In virtual memory, the file is laid out contiguously. So to calculate where the page is that we want to read in from, you just need to calculate what the offset is from the beginning, from the base of the VM region, right? The VM region starts at 0x47000, and the page we want is at 0x48000. So we know that the page that we want inside of the file is not the first one, or if you zero index, not the 0th one, but we want the first one, the one after the first one. So here, to calculate that, we do 0x48000, so that's the V page, minus the base, so VM base 0x47000. Okay, and this tells us, this gives us 0x1000. This is the offset in file, or index in file of our page. Okay, and we want to read 0x, well, we want to read 4098 bytes, starting from index 0x1000, which just also happens to be 4098. Okay, so you just read the bytes from, I keep saying 4098, it's 4096. There we go. Yeah, so you read from byte 4096 to 2 times 4096 minus 1. Okay, you read that and you bring it into the physical page. Read into 0x A1000. That is the physical page. Okay, so you read that, you bring it into physical page. And I believe that's it, right? We bring it, now everything is in physical page. So we can then resume instruction where page fault. So then we go back to the instruction, which was this one, right? It was this one. and then we perform the instruction. Here, the instruction was to read the 5,000th bit. So we go back to here, right? So remember, the instruction, we go back to the address translation part. We were trying to, that the page fault handler is done. Now we go back to address translation, where we were trying to read from 0x48004. We got the page. We check if it's the page map. Now it is. Now it is in page table. So how do we do? Well, what do we do is we first get physical address. Save some space. It is. So get physical address plus, so from page table. And then you add that to the offset. So the adder offset from the beginning of the page, which is the adder minus the v page. Right, so here the offset is 4 because 0x48004 is 4 bytes away from the beginning of the page. So we take the physical address. The physical address is 0x A1000. We add the offset, which is 0x0004, to get the final address we're going to read from in physical memory, 0xA1004. Okay, this is the final physical address we're going to read. Okay, so yeah, address translations, we tried to translate it first. It's not in the page table. So page fault, this whole bottom section happens. Then we go back and we resume. We check if it's the page map now. It is. So we get it from the page table. It's 0xA1000. You add the offset from the beginning, where the address that we want is from the beginning of its virtual page. So the offset is 4. You add those two to get the physical address you want to access. So what does that look like in the diagram below? You were trying to get the 4th byte. So this byte over here. So that corresponds to the 4th byte in this physical address. All right, so that was a long sequence of events. What I do want to point out is that this top part, so this part that I'm highlighting right now, this address translation part, I did it just to review what demand paging is, but you're not actually going to implement this. This is already handled by the VM region. The VM region in the starter code already handles all of this. I think you can actually go in and look at the starter code to see where it handles this. Okay. What you will have to implement is you'll have to implement the page fault handler. So this is the important part that you need to implement. And the starter code will call your page fault handler. This page fault handler, you have to pass in when you create the VM region. So inside the VM region, you also store a little, page fault handler. It's just a function that's called every time there's a page fault. Okay, cool. Let's take a look at, let's just quickly walk through the rest. I think we've gone through enough for this video, but let's just quickly go through the rest. We create another M file, mcrypt file, mfile2. It's connected to recipe.txt. We initialize a VM region for it. Oh, not yet. Remember, the constructor does not initialize the VM region. It just sets it to null pointer. We don't touch the physical memory. It only gets created once, and then we never, ever create another one. Okay, now, so that's the constructor. That's this line. Now we call map. Remember, map is the one that is creating the VM region. So now, map. I'm not going to draw the blue arrow because it's technically not a pointer. So this is your VM region. You have to put in a page fault handler. When you construct the VM region, you have to yourself provide a page fault handler. And then virtual memory is just 2 slots, 0x77. I feel like I'm not using diverse enough numbers. 0f000 and 80. Okay, there we go. So then the base if we were to call get base, this is not a variable that you store, but you can easily get it from the VM region. 0x7f000 get size is 2 times 4096. Even though we pass in 0 for the parameter, you always allocate it at least to the size of the file. Okay, so let's say the size of the file was, I forgot what I said, was 6,000 bytes, and then we just round up to the nearest page. Okay, so let's walk through the steps one more time. We access in index 5000. So this, the base is 0x7f000. So this recipe pointer is 0x7f000. So then what would recipe at index 5000 be? What address is that? That is 0x8 4009. Oh, okay, 4096. So it's just 8000. Nope, too many zeros. No, that is the right number of zeros. 4. Okay, so the 80 at the beginning was not intentional. It's only the last 3 zeros that form the offset. The 80 at the front is the actual page index. So we have the 80 here. Now we walk through the sequence up here, address translation. So 0x, we want 0x80004. Okay, just to make the offset a little different, let's change 5000 to 5010. So the address here is instead 000A. Okay, so the address translation is now 0x800A, 0x800A. So the V page is 0x80000. Check if it's in the page map. It's not, right? It's not in the page map down here. Not in the page map down here. So page fault. So we go to the page fault. Yeah, we allocate a page. So let's allocate the page. Let's use purple. Allocate a page. Suppose we get this one. Remember, they don't have to be in that order. The page algorithm can do whatever it wants. So allocates that page. Okay, we update the page map. So we get the mapping 0x. Our virtual address of our virtual page is mapped to 0x84000, read write 1. Remember, any change you make to the page table, also store it in your supplemental page table. Read write 11 m file 2, because this is from m file 2. And then we're done with this step. Bring the contents into the physical file. So here you have to use, I never wrote what you have to use for this one. You use aligned p read. Okay, so you go to the file, you use aligned p read to read from the file into 0x84000. Okay, now how do you know which index in the file you want to read from? Well, you do the math again, right? You do 0x, you do the, what was it? The virtual address, which was 0x8000, and you might subtract it from this one. Okay, and the offset is still the same. We still get the offset of 0x1000. So that's the actual index in the file you want to read. Okay, so you paste that in, and then your page fault handler is done. Now you go back to the address translation. Is it in the page map? Now it is. Now 0x8000 is in the page map. You get the p page, and then you add the offset. The offset here for this one is, the offset is 000A. So you just add the physical page to 0x000A. So the final p page should be, sorry, no, not the final p page. The final physical address should be 0x8400A. So this physical address is actually 0x8400A. Right. This physical address we said was 0x8100. 4. Okay, cool. And then we write a queue. So you go to that address. So offset something here. Purple is here. and we write a queue here. Now, virtual memory, remember, it doesn't actually exist. It's just what the programmer imagines the memory looks like. The actual change happens here. Queue. Okay, oh, that was a lot. All right, let's do this next one super quickly. In fact, I want you to pause the video and run yourself through the sequence of events. What happens when you run memset of book plus 6 times 4096, x and 5000. So what this means is at index 6 times 4096, I want you to write x, the character x, 5000 times. Pause the video, try walking through that yourself. Okay, I'm going to assume that you have already, so I'm just going to quickly go through the answer. This is going to be a long. Actually, instead of going through all the steps one by one, which I assume you already did, we're just going to jump right in. I'm familiar with the steps enough. I've tried recording this video so many times that I can walk through this by memory. So let's go. So 6 times 4096. So that is 0, 1, 2, 3, 4, 5, 6. So we're writing into this one. This one. So let's use yellow. This one. Okay, so what are the steps? Well, first, not in page map, so page fault. Then we allocate a page. Okay, let's allocate A3. We add it to the table. So 0x4d000 gets allocated to 0x A3000, read write 1. Same thing down here, 4d000, 0xa3000, read write 1, 1m file 1. I'm tired, so I'm just speeding through this. Okay, page in. Offset, you know how to calculate that. 0x4d000 minus 0x47000. That should give you whatever 6 times 4096 is. You read from the file starting at that index and you read 1 page. Read that into this file. Now address translation resumes. You check if it's in the page table. It is. You get the page for the physical page, and then you add the offset. Now, memset doesn't just change one single address. It actually is a while loop that goes through a bunch of addresses. So the very first address it tries to access is 6 times 4096. This thing I think is 0x4d. Yeah, so it first tries to access that virtual address, page fault. And then it brings the page in, and then it successfully writes X. Then it goes to 4D001. Now there's no page fault because 0x4D000, that's the page, is already in physical memory. It's in the page table. So no page fault there. And it's not going to have a page fault with all the X's that you write until you get to the next page, 0x4E000. So and what happens here is there's just a bunch of X's, right? This page gets filled up with X's. So this thing gets filled up with a bunch of X's. Okay, and then finally, you get to the next page, 0x4E000, right? That is a completely different page. If you clear the last 3 hex digits, you get 0x4E000, which is different. So check the page table, not in page table, so page fault. First step in page fault, allocate a page. So page alloc, we get A2. Next, update the page table. Okay, 0x4E000 map to 0x A2000, read write 1, 0x4E000, 0xa2000 R, read write 1 M file 1. Now, this page, okay, now you have to do the p read, align p read thing again. You do the offset to get the index, blah, 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 blah. You get this one. Okay, now, because we write 5,000 times. So we wrote 4096 times in the previous page. In this page, we just have to write it 4 more times. So 4 more X's. Let's use red. X, 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 X. So 4 X's, X, 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 X. Okay, the first X in that new page has a page fault, right? That's how we added the page map. But then all the subsequent X's don't have page faults because they're still in the same page. So that page was already mapped. Okay, so what's important about, okay, we have it mostly done. This is how virtual memory works. This is how demand paging works. And this is what you'll be implementing. These steps that I went over, you will have to translate into code so that your picture, this picture does all those steps and gets you to this state. Okay, so when you're lost, try drawing this picture yourself. In fact, right now, just pause the video and draw this picture from scratch, run through this code again and see if you can recreate this picture. Okay, might be a nice exam question, right? Recreate this picture. But once you're able to do that, when you write your code, you can then check what code did you write and how that changes the picture, and just make sure that the picture gets to the right state. This diagram needs to look like this. Okay. We don't have any other lines of code. Oh, we have to talk about the flush. Oh, okay. Forgot about the flush. I thought I could end the video already. One thing I want to note is physmem is full now. So if I try to read another page, it's going to do the whole page fault thing. And then you will try to, in your page fault handler, you will call page alloc. And that will return null pointer because there's no more pages. What happens in a real operating system? You would pick a page to evict. You don't have to do that yet because you'll do that next week. Yeah, so you don't have to do that yet. We'll actually talk about, I have a suggestion for how to decompose that page alloc part. So I'll talk about that in video 2. Yeah, but just wanted to point out that, physical memory is full, but for this project, you can assume that you will never go past the physical memory limit. All right, let's talk about flush. So what should flush do? Well, flush needs to look at which pages were modified, and it needs to take those pages that were modified and write the physical memory back into the file. Okay, so notice here, we've modified a lot of stuff here, but we never actually changed the file, booktx.txt. So if we called mfile1.unmap, sorry, not unmap, .flush. When you call flush, the first thing you have to do is you have to see which pages were mapped by the mfile1. And we know that it's the red page, the yellow page, and the blue page, right? Red, yellow, and blue. But the thing is, how do you figure that out? Right? Like in physical memory, that's just a bunch of bytes. You don't know which pages belong to which files. Right. You only know the correspondence between the VM region and the physical memory using the page map, but you can't access the page map. You can modify it, but you can't read it. Right. Do you see where I'm going with this? The supplemental page table below is how we figure out which physical pages and which virtual pages belong to each file, or which file does it belong to. So here, when we try to flush mfile1, which pages do we need to flush? You can just check which ones are mfile1, these 3. So you just need to flush this physical page, needs to go back into this file. This, not that one, this one needs to go back to mfile1, and this file needs to go back to mfile1. So let me actually write that out. Flush. Find all pages that need to be flushed using sup page table. Okay, now you know what file it is, right? Because you have mfile1. mfile1 has the book, so you can call. So the last step is going to be flush or write. P aligned, P write allows you to write to the file. But the question is, where in the file are you going to write to? Beginning, end, somewhere in the middle? Yeah, you don't know. So how do you figure out where? Pause the video, see if you can figure that out. This is a good exam question. Okay, did you figure it out? It's very similar to how we initially figured out where from the file to read from, right? This vpage entry, this vpage tells us where does this page belong in virtual memory. In virtual memory, the entire file is contiguous. So if we know that this virtual page is 0x4800, the base is 0x4700. So we know that this page inside the file is like the second page. It's the one after the first page, right? Well, here you can calculate that this page is the 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. The seventh page, or index 6. This page is index 6 inside the file. So the true index inside the file is 6 times 4096. It's the sixth page, or 6 times 4096. That's the index. So just exactly the same as when we read it. We used the virtual page to determine. You compare the virtual page to the base to figure out where in the file it is. Same thing when you write it out. So, same thing, right? 0x48000, B page, minus 0x47000. That's the VM base. This gives you the index in file, which is 4098 for this one. So you have to write 4098 bytes of this physical page. So write 4096 bytes of this physical page. So the red contents, you have to write that into index 4096. Keep mixing 4096 and 4098. 4096 into index 4096 of size 4096, one page. If you were to write this one, if you were to write this one, the yellow page, that would be at index 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 6 times 4096. So you would write into the file at index 6 times 4096. How many bytes do you write? You write 4096 bytes, one page. And you write the yellow contents here from A3, you write it back to the file. Cool. All right, that is the flush. And we are done. We have gone over address translation, paid full handling, and flush. And I've also gone over how do you implement the constructor. In the next video, I will go over the starter code and sort of give you a little bit more hints as to how each of these steps look like in code. Although honestly, this is basically the pseudocode. You should be able to code this up just by looking at this. So before we watch the next video, try to code this up. Look at the starter code, try to figure it out on your own, and then use what we went over to try to code it up. All right, I need to find a charger. I'll see you in the next video. Bye.